remember that the main reason why we're doing any of this stuff goes back to the very first day of exploring this, when we did our little graphing thing, when I tried to mess with you and make you think that it was y equals x, but it really, remember that? And remember how I described you can take just about any function that's not a polynomial, like sine of this and e to that and ln of such and such, whatever. You can take just about any function like that and you can turn it into a polynomial, right? And depending on how many terms you have, it'll affect the accuracy of that polynomial in representing the original function. We talked about kind of that interval of convergence idea. Remember on the graph where the interval of convergence seemed to get larger and larger for some graphs. I talked about how sometimes it doesn't. So the whole reason we're doing any of these, does it converge, does it diverge, is ultimately we are going to be making decisions about how good of a fit is that polynomial to the original function. That makes sense? How good is the fit? Is it great? Is it terrible? Is it great but only for like a small interval? Is it for a large interval? And how does it all work? What about the endpoints of the interval? How do those all work out? So we're trying to build some skills so that in the not too far off future, when we start asking questions like that, like how good was the approximation really, we'll have some tools to be able to answer that question. And then, of course, these series, that these polynomials, or eventually we'll call them series, can take on all kinds of different forms. And so we need lots of different tools to be able to decide, does this series actually converge or does it diverge, right? So do you guys remember the two tests that we did several days ago? Nth term and geometric. What is the only thing the nth term test really could possibly even tell us? Yeah, it's going to diverge, and if it might converge, it just doesn't say anything. Stands there, grumpy, right? The geometric series test, a little more balanced. It'll tell you convergence or divergence, but it's extremely narrow in scope, right? This is like one of those, like maybe if you had a coach and the only thing they coached you on, the only thing they knew how to coach was how to do a proper squat in the gym, right? Because if you've ever done squats, you know there's a lot of ways to screw those up, right? A lot of ways to injure yourself, a lot of ways for them to go bad. So if you get a coach that knows all the stuff you need to know about squats, they could coach you up really well on that, but nothing else. You ask them about, bench press or power cleans, and like, I don't know, I'm really good at doing squats and coaching squats. That's kind of like geometric series. It'll tell you good or bad or whatever, but only about geometric series. Make sense?
Yes.
Okay, so then last time we talked about the integral test, and the integral test is a test that you can use, that maybe you should use. I mean, we'll start to make these somewhat subjective judgments on should we use it, yes or no. Maybe it's the right choice, maybe it's not. That could even be a matter of opinion. But the bottom line is to be able to use the integral test, the series that you're trying to work with, it has to have an nth term that's easily integrable, right? And if you look at it and you think, there is no way I could find the antiderivative of that, you probably shouldn't use the integral test, right? Because you're going to be doing an antiderivative in the midst of this. So if you look at it and you're like, you know what, I know what the antiderivative is, maybe I could use this test, that'd be a good idea. The conditions are that the function describing your series has to be positive, continuous, and decreasing for the domain of the series that you're working with. And we talked a little bit about that during our proof. And here's kind of the essence of the integral test. If you do the definite integral from 1 to infinity, and of course that is an improper integral, and you get a real number of any kind, you get some real number, that means that the improper integral converges, therefore the series converges as well. But if you calculate this improper integral out and you get a diverging answer, like infinity, then that means that the original series also diverges. They're going to follow suit. One's going to follow the other. We're going to always be finding the integral first, and so we could say that the series behavior will follow the integral's behavior. That make sense? All right. So a couple more things here I want to mention to you before we dive in and do some examples. There are some potentially easier ways to do this, and one of them we've talked about a little bit. I'll come down here, and we'll talk about the P series and the harmonic series. So as you guys maybe remember from before, a p-series is specifically this, where your nth term is 1 over a variable, probably n, right? 1 over a variable to a numerical power. So things like 1 over n squared, 1 over n to the 5th, 1 over n to the 1/2, 1 over n to the 4/3, those are all considered to be p-series or power series. P for power typically, but we usually use the letter P because power series is actually more of a broad general term. Those are all examples of p-series. And if you remember from before, a p-series converges if p is bigger than 1 and diverges if p is essentially less than or equal to 1. If p is less than 0, then this would actually fail that nth term test, right? The terms would be getting bigger and bigger and bigger, so it wouldn't even make any sense. So maybe you remember that p-series. So this one's really simple. Like if you look at one of these and you say, look, p equals 5. That's bigger than 1. Therefore, this series will converge. A p-series, if you can find a p-series and you use this test, it's really easy, right? I mean, that's the one condition. How big's p? Is it bigger than 1 or is it less than or equal to 1? If you can make that decision, p-series pretty easy. Sometimes people will kind of misconstrue this and they will think that they can use the p-series on anything. So kind of like the geometric series, the p-series is balanced. It'll tell you convergence or divergence, but it's incredibly narrow in its scope. For example, you might see something like this as an nth term of a series. And you say to yourself, cool, p is 2, bigger than 1. Therefore, by the p-series test, this converges. Pause. That's not a p-series. What messes it up? Plus 1. Now, there's ways to deal with this for sure, varying difficulties, but that's not a p-series. So don't try to use a p-series test on that. Another example, I mean, I'm sure you'll get this one. What if you have 1 over n squared plus n minus 5? Somebody might look at that and say, look, p is 2 by the p-series test. No, it's not a p-series. It has to be 1 over n to the some number, and that's it. That's what makes it a p-series. Question, John?
So why on the R test, R can be greater
On the
than
R test.
Geometric.
Geometric, okay, yeah.
Yeah, geometric series test. Why can R be greater than or equal to 1, while this one is going to be less than or equal to 1 for it to apply? Like, what makes it equal then?
Well, so they're just different animals. I mean, I hate to say it that way, but like, so these are all essentially 1 over a variable to a numeric exponent, right? But a geometric series is kind of the opposite. A geometric series is 1 over a numerical base to a variable exponent. Does that make sense? Now, if you want to go, like, there's some really deep places we can go here on the why is it this way and why is it that way. And then you're going to be starting to delve into what you call analysis, like an analysis course, or sometimes it's called like advanced calculus, I guess. And it's way beyond the scope of our class. Like if you thought the proof that I showed you the other day was like, it's going to be rough. Right, so this is like, so the analysis class, like analysis 1 is usually either a class that you've taken after Calc 1, 2, 3, Diffie-Q, linear equations, maybe modern algebra, or first year of grad school. So some of the whys that you might ask, I might be able to give you a pretty quick answer. Others I'm going to say, do we have like a month for us to like do like a rough analysis intro, and then maybe you might possibly sort of maybe understand it? In that case, I'm going to be like, you know what, let's just move on. They're just different, I'll probably say. Does that make sense? I got to kind of pick and choose my battles.
Does the test work if it's like 1 over 3n?
Sure. So if you had...
So there just could be another...
Well, so if you had... I think I know what you're talking about. So let's say you had... I'll give you the whole thing. Let's say you had sigma, I don't know, from like n equals 1 to infinity of 1 over... Now is... Colin, I want to make sure I've got this. Maybe it would be 3n to the 5th. Is this basically what you're saying? Anybody know what you could do to make this a... you could make it an obvious p-test. I heard you say take, so I'm going to assume that's what you meant. Right. You could make it an obvious p-test by doing that. Does that make sense? Okay, Dylan, go.
If you had like 3 into the 5th plus 2 in, but then you wrap that all in parentheses and squared it, just because it's still a single term, does that apply, or does it have to be?
That would not be a p-test. You'd have to FOIL that thing out and use a different approach. Yeah.
You have a series like the formula 1 over 2 to the p plus 1.
Okay, hey guys, could you quiet down just a little bit? I'm having a hard time hearing Matt. Could you say that one more time?
Yeah, if you have a series like 1 over, oh, you don't know, that's a stupid question.
I'm not saying it is.
Well, it was, I was asking if it was still a p series, but it's a geometric series.
So, are you sure?
Yeah.
Oh, like, 2, you said 2 to the p?
Yeah.
That is, or 2, maybe like 2 to the n or something. That would be a geometric series. Yeah. These are all the questions you got to sort through, right? Because we kind of settle on our favorite approaches, and then we get thrown a little curveball, but it's not really a curveball. It's just different than the way we've been thinking. So we need to ask those questions. I'm glad you figured it out. Anybody else? Okay. So the other piece here is, I want you guys to realize, like if we go back here and we said, like if you had sigma from n equals 1 to infinity, and then in here you had something like 1 over n to the 4th, when you look at that, would you guys agree with me that 1 over n to the 4th would actually be a pretty easy antiderivative? So if somebody looked at this, they could say, you know what, I would like to do the integral test and do the improper integral from 1 to infinity of 1 over n to the 4th and go through all those steps, and they'd get a good answer. They really would. But wouldn't you also agree with me that it would be way easier to say, hey, that's a p-series, and p is 4, and that's bigger than 1, therefore I'm done, right? Instead of going through all these integrand, antiderivative, limit, FTC, right? It's a lot easier to identify it as a p-series, identify what p is, how it relates to 1, and then you're done, right? So similarly, this next one, I know it just looks like it's sort of a footnote, but you're going to find that as we wrap this unit up on into like February and March, this one right here, the harmonic series, is going to become one of the more important tools that you have in your toolbox, okay? So I want to make sure you understand what it is and what it means. Yeah, Josiah.
Sorry, just real fast. With the p-test, if it converges, if we know that the p term is greater than 1 and it meets all its conditions, are we still allowed to do the 1 over p minus 1 thing to find the value?
Or to actually find what it is, only if you would be called upon to actually say, and the sum of the series actually is,
Okay. And
which would be a rare, I think it'd be rare,
Okay.
but it wouldn't be wrong.
All right. Is that the thing? It's 1 over p minus 1?
You can tell that I don't use it very often.
I think so.
That sounds right.
I think so.
That definitely sounds right. I'm visualizing that thing we saw in Unit 8, but I use it so rarely that I would just look it up. Okay, so here we go. So a harmonic series is any series. So again, please don't read more into this than is there, right? Don't blow this up and say, oh, so then all this stuff is a harmonic series. Harmonic series is incredibly narrow in scope. This is the base form of a harmonic series, 1 over an plus b. So some examples of harmonic series would be this. If your nth term was 1 over 2n plus 5, or 1 over 3n plus 1, or 1 over 7n plus 6. I don't know. You can start to see the pattern. 1 over an plus b. That is what we call a harmonic series. The most generic form of a harmonic series is when a is 1 and when b is 0. So that's what I've got up here. A harmonic series is a specific form of the p series when p is 1, right? You can see the p is 1, but then we can extend it into a more general form of 1 over an plus b. So we could show pretty easily, like if I just took this one, we could show pretty easily divergence on these. So here's the short story, is that all harmonic series diverge. And so this is a lovely fact, because if you know what a harmonic series is, you can name it and say, that's a harmonic series, and they always diverge. As long as you're using that terminology, that's sufficient proof, right? Sufficient proof to say that whatever series it is diverges. Now, if you look at it and you say, well, that's one of those such and such a music-y sounding series things, so it diverges, you got a problem, right? You're going to have to go back and use like the integral test or something like that. But if you can say, that's a harmonic series, and I know what that's all about, and it diverges all the time, we're good. Okay? So let me just give you an example of why this harmonic series diverge. I'll just do that first one. Integral from 1 to infinity of 1 over 2n plus 5 dn. And maybe you'll see this pattern emerge here. I would go limit as b goes towards infinity. Integral 1 to b, 1 over 2n plus 5. What's the antiderivative of 1 over 2n plus 5? There you go. So it'd be limit as n, or b goes towards infinity of 1/2 ln of 2n plus 5. The absolute values really don't need to be there, because I know my n is going to be positive, and so 2n plus 5 will always be positive, so I'll drop those in a second. Then you have limit as b goes towards infinity. It would be 1/2 natural log of 2b plus 5 minus 1/2 natural log of 7. So then what happens when I do this limit as b goes towards infinity? Wouldn't 2b plus 5, which is the only thing the limit really applies to, wouldn't 2b plus 5 get really huge? And what's the natural log's output if the input is really large? Yeah, similarly large, right? ln just continues to increase, albeit at a decreasing rate, but it does, ln's graph does continue to increase. So we would say that this would be infinity minus 1/2 natural log of 7. And of course, 1/2 natural log of 7 doesn't have a prayer against infinity. Sorry. And so you just end up with this diverging answer. So again, if you can recognize a harmonic series like these right here, you can choose to do the integral test, just like I showed you. And maybe you'll do some of these in a little bit. Or you could look at it and say, hey, that's a harmonic series, and they always diverge. Done. Just stop. Don't ramble on. It's harmonic. It diverges. Done. Yeah.
It was equal to like negative negative 1.
So all the series we've dealt with so far have been series in which all the terms are positive. So I guess it'll be next week? I think it'll be next week. We'll start to talk about, well, what if some or all of the terms were negative? What do we do then? We'll get there. We'll get there. Okay, any other questions?
If any of, can you say if the function is increasing then it diverges? Like just generally?
Well, that would be the nth term test, right?
Oh.
Right, so if you go limit as n goes to infinity of whatever the nth term is, so I'll put it like this. So you go limit as n goes towards infinity of a sub n, where a sub n is just whatever the nth term is, and you get anything other than 0, automatically the series diverges. Remember, that's that coach that will only yell at you negative things, right? You're going to diverge. You loser. You're going to diverge. They're really mean. I don't know. Maybe they're not. But they'll tell you about diverging. That make sense?
That makes sense.
Okay. All right. So I have a set of questions here, and I don't exactly know how far you're going to get through these. I would love it if you got through all of them, because if you are super efficient, I think you could do that. I'll give you a little bit of time here and see what you can do. Maybe you pick out the easiest looking ones. You basically have 1 through 5, I think. Yeah. So there's 1 through 5. And some of these, I think, based on what we've been talking about with P-series test, integral test, and then the identification of a harmonic series, some of these should be super easy and won't take you very long. Others might take you a little bit longer. But you could easily take some of the ones that shouldn't take very long and make them take a lot longer if you chose a less efficient route. So do what you want to do with these. You're equipped with hopefully some good information. Give them a shot. Yeah. Yes, sir. Let's try to identify the ones that you could actually do very quickly, because there's a handful of these you could. Number one, I would say couldn't do it super quick. Dylan's giving me the stink eye. How would you do that one super quick? So my definition of super quick, and this could be different from yours, my definition of super quick is don't make me do an antiderivative. Don't make me do a limit. Don't make me do all that stuff. I just, like, when I say quick, I literally mean bam, bam, done. Not step 1, step 2, step 3, step 4. I agree. I'm not saying that one is like really super incredibly difficult. I'm just saying quick. Number 2, I think, could be done very quickly. What I would say with number 2 is, I would just say this, is a harmonic series, therefore it diverges. You could go through a lot of steps on 2. You could actually do a p-series test on number 2, right? You could also say, is a p-series and p equals 1, therefore the series diverges. You could also do an integral test. To me, that would be the least desirable. Josiah.
So would anything like 1 over 1 to the first power be a harmonic series?
Yeah, that's the most basic harmonic series.
So because you could have like 2 and the b term 0.
Yeah. If it was 1 over 2 and I just get the 2 out of there as a 1/2, and now we're back to this. Make sense? Okay, so there's that one. I would say, guys, number 3, not ultra quick. Again, not like insanely difficult, but not ultra quick. I would say number 4 should be ultra quick. What kind of a series is number 4? That's right. So I would say this is a P series. Notice how I'm naming a lot of stuff. I'm not just being generic and saying diverges. Hey, again, listen carefully. I said this before. I think it's probably warrants saying again. Remember that for most of these scenarios, including when we get into later stuff with power series and all that stuff, listen, there's going to be 2 possibilities, guys. Converges or diverges. I'm not interested in awarding credit for converges. Oh, I was so lucky. So you are going to want to be like rigorous and thorough with how you explain yourself, right? So that's what I'm trying to model for you. So I'm saying that series is a P series, and P equals 4/3. Am I ready to make a conclusion? I need to relate it to 1, right? So I need to say it's greater than 1. That P value is greater than 1. Therefore, now I can conclude, therefore, the series, or you could write out the actual series notation there, converges. Because P is bigger than 1. Okay? So again, it's a 50-50 shot, and I'm totally disinterested in just awarding credit because you got lucky. And the only way that I know that you didn't just get lucky is if you explain yourself thoroughly. Sort of like that. Yeah?
Do you want us to name the series or the test that we use or both?
You could go either way. I called it a P series, so I think it's a little redundant to say I use the P test. If you want to put both in there, obviously that's no problem. You really have to do one or the other. Like with the integral test, it's not like it's an integral test series. So you'd have to say, hey, I used the integral test, and here you go. Or, hey, it's a geometric series test, right? This is a geometric series, therefore. So you're going to want to name it in some form or fashion. Probably don't have to double name it.
Is that okay?
Oh, yeah, for sure. Yep. And that harmonic series stuff is totally fine. Like on an FRQ, if you just say, hey, that's a harmonic series, I know it diverges, that's good. So that's totally fine. Okay, so I need Emma and Cole to make a very, very